Welcome to Module 6, where we begin our examination of search algorithms and optimization in artificial intelligence. In this module, we are shifting attention to a different kind of intelligent behavior, the ability of an AI system to reason through possibilities, compare alternative paths, and move toward a solution even when the answer is not immediately available. That distinction matters because many people associate artificial intelligence mainly with machine learning, where systems learn patterns from data. Search algorithms operate from a different starting point. They focus on how a system can explore a structured space of possible decisions, actions, or outcomes, and then identify a path that is optimal, near optimal, or simply good enough for the problem being solved. When we talk about search in artificial intelligence, we are really talking about problem solving under structure. A problem is not treated as a vague question or an open-ended guess. Instead, it is represented as a search space, meaning a set of possible states and the transitions that connect one state to another. A state can be understood as a particular condition or configuration of the problem at a given moment, while a transition represents a move from one condition to the next. Once the problem is represented in this way, the AI system can begin traversing that space, examining possible routes, and determining which sequence of steps leads toward a desired outcome. This is why search algorithms are foundational to artificial intelligence. They give systems a formal way to explore alternatives rather than relying on random trial and error. In many AI problems, the system is not handed an explicit solution in advance, so it must work through the available possibilities in a disciplined manner. The challenge is that the number of possible paths can become very large very quickly, especially when each decision leads to several new options. A search algorithm provides the method for navigating that complexity, deciding what to examine, what to postpone, and what may be unnecessary to pursue. This slide also emphasizes that search algorithms help identify optimal or near optimal outcomes. An optimal outcome is the best solution according to the criteria of the problem, but in complex settings, finding the absolute best answer may be expensive or impractical. In those cases, a near optimal solution may still be valuable because it produces a strong result within reasonable time or computational limits. This is important in artificial intelligence because intelligence is not only about getting an answer, it is also about managing the cost of reaching that answer. A system that finds a perfect solution too late may be less useful than one that finds a very good solution efficiently. The idea of systematically navigating a problem space also helps us understand how AI systems support decision making. They do not simply jump from question to answer. They evaluate possible paths through a structured environment, and each movement through that environment reflects a decision about what direction to explore next. In a path-finding problem, this may involve moving from one location to another. In a planning problem, it may involve deciding which action should happen first, which action should follow, and how each decision changes the state of the system. In each case, search makes intelligent behavior possible by connecting representation, exploration, and decision making. It is also important to notice that search becomes especially useful when explicit solutions are not immediately available. If the answer were already known, there would be no need to search. Search is needed when the system must discover a solution by exploring relationships among possible states. That is why the structure of the problem matters so much. The more clearly these states and transitions are represented, the more effectively the system can move through the space and evaluate what it finds. Poor representation can make a search problem harder than it needs to be, while a well-designed representation can make intelligent exploration much more manageable. As we begin this module, keep in mind that search algorithms are not separate from intelligence. They are one of the mechanisms through which intelligent systems act. They allow AI to move from uncertainty toward resolution by examining possibilities in an organized way. They support the search for solutions, the evaluation of alternatives, and the selection of actions that advance the system toward its goal. This is the foundation for the rest of the module, because once we understand what search is, we can begin comparing different search strategies, examining how heuristics improve efficiency, and exploring how optimization techniques extend search into more complex problem spaces. That progression will help us see search as both a practical tool and a conceptual framework. This slide introduces the concept of search algorithms in artificial intelligence, and it gives us the foundation for understanding why search matters as a form of intelligent problem solving. In artificial intelligence, a search algorithm is a systematic method for exploring possible solutions when the answer is not immediately available. The system is not simply guessing, and it is not waiting for a solution to appear from training data. Instead, it moves through a structured set of possibilities, examining what option exists, how those options connect, and which sequence of decisions may lead to an optimal or near optimal outcome. The slide emphasizes that search algorithms enable AI systems to explore possible solutions, and that idea is central to how many intelligent systems operate. A problem often contains many possible directions, but only some of those directions move the system closer to a useful result. Search provides the procedure for navigating those directions in an organized way. This is especially important in situations where the system cannot directly compute the final answer in one step. It must consider alternatives, compare paths, and continue moving through the problem space until it reaches a solution that satisfies the goal. A major idea here is that search algorithms help identify optimal or near optimal outcomes. An optimal outcome is the best possible solution according to the conditions of the problem, while a near optimal outcome is a solution that may not be perfect, but is still highly effective. In real artificial intelligence applications, this distinction matters because perfect solutions can sometimes require too much time or too much computation. A system may need to find a strong solution efficiently rather than spend excessive resources trying to prove that no better solution exists. Search algorithms give AI systems a disciplined way to manage that trade-off. The slide also notes that search focuses on systematically navigating a problem space. A problem space is the structured environment of possible states, actions, and transitions that define the problem. A state represents one possible condition of the system at a particular point, while a transition represents a possible movement from one state to another. When an AI system searches, it is moving across this structure rather than acting randomly. It examines how one state can lead to another and how a sequence of transitions may eventually produce the desired outcome. This is why problems are represented as search spaces. The representation gives the AI system something concrete to work with. Without a search space, the problem remains too vague for systematic exploration. Once the states and transitions are defined, the system can begin to reason through the available possibilities. It can determine where it is, what actions are available, what new states those actions create, and whether those new states move the system closer to its goal. In that sense, search is not just a technique for finding an answer. It is also a way of structuring the problem so the answer can be discovered. This slide further explains that possible states and transitions define the structure of the problem. This means that the quality of the search depends heavily on how the problem is represented. If the states are poorly defined, or if the transitions do not accurately reflect what can happen, then the search process may become inefficient or misleading. A well-structured search space allows the AI system to explore meaningfully because each movement has a clear relationship to the larger problem. The system can then evaluate possible routes and avoid treating the problem as an unorganized collection of choices. Finally, the slide connects search to intelligent decision making. AI systems traverse search spaces to support decisions because each step through the space reflects a choice about what to examine next. The system may be trying to find a path, solve a planning problem, optimize a sequence of actions, or identify a solution under constraints. In each case, search allows the system to move from uncertainty toward a result through structured exploration. That is why search algorithms are considered foundational in artificial intelligence. They show how a system can reason through possibilities, evaluate alternatives, and act intelligently when explicit solutions are not already available. This foundation will matter throughout the rest of the module because later search strategies build on this same basic structure. Whether the method is blind, heuristic-based, or connected to optimization, the system still needs a problem space to explore and a way to move from one state to another. Once that structure is in place, artificial intelligence can transform a difficult problem into a sequence of manageable decisions. Search gives the system a path through complexity. Now that we have established search as a way for artificial intelligence systems to move through a problem space, we can begin distinguishing between two broad families of search strategies: uninformed search and informed search. This distinction matters because it tells us whether the system is exploring the problem using only the structure it has been given, or whether it's also using some additional guidance to make that exploration more efficient. In both cases, the system is searching through states and transitions, but the way it decides what to examine next is different. That decision process can affect how long the search takes, how much computation is required, and how practical the method becomes for complex problems. Uninformed search strategies are often called blind search strategies because they do not use extra knowledge about which path is likely to be better. The word blind does not mean that the algorithm has no structure at all. It still knows the available states, the possible transitions, and the rules for moving through the problem space. What it does not have is guidance that helps it estimate which option is closer to a goal or more promising than another. As a result, uninformed search follows a general rule for exploration rather than making an informed judgment about the quality of each path. This makes uninformed search useful as a conceptual foundation because it shows how an AI system can solve a problem using only the formal structure of that problem. If the search space is small, or if the structure is simple enough, a blind search strategy may still reach a solution effectively. The limitation appears when the number of possible states becomes large. Without guidance, the system may spend substantial time examining paths that are technically valid but not very useful. Informed search strategies take a different approach because they incorporate heuristics into the search process. A heuristic is a form of guidance that helps the system estimate which paths are more likely to lead toward a useful solution. It does not guarantee perfection by itself, and it is not the same as already knowing the answer. Instead, it gives the algorithm a way to prioritize the search space so that it can focus earlier on areas that appear more promising. This is why informed search is described as heuristic-based. The search is still systematic, but it is guided by an additional source of knowledge. The slide emphasized that informed search uses heuristics to guide the search process, and that additional knowledge can improve problem-solving performance. That improvement comes from reducing wasted exploration. When a system has a reasonable estimate of which direction is likely to be productive, it can avoid treating every possible path as equally attractive. This does not mean it ignores the structure of the problem. It still depends on states, transitions, and goals, but it adds a layer of evaluation that helps the search become more selective. The contrast between uninformed and informed search clarifies the role of knowledge in artificial intelligence. Uninformed methods show what can be done with structure alone, while informed methods show how performance can improve when the system has some way to assess the promise of different choices. In a complex problem space, the same goal may be reachable through many possible routes, and the cost of exploring all of them can be extremely high. By introducing heuristics, informed search gives the system a practical mechanism for deciding where attention should go first. It's helpful to understand this difference as a continuum of guidance rather than as a simple judgment that one approach is always better. Uninformed search can be valuable when little information is available, when the problem space is manageable, or when we need a baseline strategy that does not depend on assumptions. Informed search becomes more powerful when the heuristic is meaningful and aligned with the problem. However, poor guidance can also mislead the search, so the quality of the heuristic matters. The central point is that informed strategies use additional knowledge to improve problem-solving performance, while uninformed strategies rely only on the problem structure and search without that extra direction. As we move forward, this distinction prepares us for a deeper look at heuristic-based search. Once we understand that heuristics provide guidance, the next question becomes how that guidance improves efficiency. Efficiency is about reducing unnecessary evaluation, managing computational effort, and reaching useful outcomes with fewer wasted steps. That is why the difference between blind search and heuristic-based search is one of the core ideas in artificial intelligence problem solving. It shows how the same search space can become much more manageable when the system is given the right kind of information to guide its exploration. This slide moves us from the broad distinction between uninformed and informed search into the specific question of why heuristic-based search can improve efficiency. The important idea is that efficiency in search is not only about finding a solution, it is also about how much work the system must do before it reaches that solution. In artificial intelligence, many problem spaces become extremely large because each possible action can create several new states, and each of those states can create still more possibilities. If the system explores too many possibilities without guidance, the search process can become slow or impractical. Heuristic-based search addresses that challenge by helping the system focus on parts of the problem space that appear most promising. The slide states that heuristic-based search reduces the number of possible solutions evaluated, and this is the central efficiency advantage. A search algorithm may have many paths it could examine, but not all paths are equally useful. A heuristic gives the system a way to estimate which options deserve attention earlier in the process. Instead of moving through the search space blindly, the system uses guidance to make exploration more selective. This does not mean the system already knows the correct answer. It means the system has a practical way to avoid treating every possible direction as equally valuable. This guidance often comes from domain-specific knowledge or estimation techniques. Domain-specific knowledge refers to information about the nature of the problem that helps the system judge what is likely to work. Estimation techniques approximate the value, cost, or promise of a possible path. In both cases, the system is using more than the basic structure of states and transitions. It's adding a layer of judgment that helps prioritize the search. That added judgment is what allows informed search to become more efficient than blind search in many complex situations. The slide also notes that heuristics allow AI systems to prioritize promising paths. This point is especially important because search problems often involve branching. At each stage, the system may have several possible moves, and each move may lead to a different region of the search space. Without a heuristic, the system may spend time exploring paths that are valid but unlikely to lead to a strong result. With a heuristic, the system can examine paths that appear closer to the goal, less costly, or more aligned with the desired outcome. The result is a more directed form of exploration. Heuristic approaches also help avoid unnecessary computation. In artificial intelligence, computation is a resource, and inefficient search can consume that resource very quickly. When a system evaluates large numbers of irrelevant or low-value possibilities, it may still be working correctly, but it is not working efficiently. A heuristic helps reduce that waste by guiding the system away from paths that appear less useful. This makes the search process more practical, especially when the problem space is too large to examine exhaustively. The value of the heuristic is tied to its ability to reduce effort without losing sight of the goal. At the same time, heuristic-based search is not simply about speed, it is about intelligent allocation of effort. A faster search is only useful if it still leads to meaningful solutions. Good heuristics support that balance by helping the system focus on likely candidates while still operating within the structure of the problem. Poor heuristics can create the opposite problem by directing attention toward paths that look promising but are actually misleading. So, when we analyze heuristic-based search, we are really analyzing how guidance affects the quality and efficiency of problem solving. The final point on the slide is that informed search can guide problem solving more efficiently than blind search. Blind search can be systematic, but it lacks a mechanism for judging which option should be explored first based on usefulness. Informed search adds that mechanism through heuristics. The system still searches, but it does so with guidance that helps reduce unnecessary evaluation and prioritize better alternatives. In graduate-level AI work, this idea matters because it shows that intelligence is often about managing complexity rather than eliminating it. Search spaces can be too large for exhaustive exploration, and real-world systems often need timely decisions. Heuristic-based search gives AI a way to operate under those constraints by using estimates, knowledge, and prioritization to make exploration more efficient. The system does not need to inspect every possible solution with equal intensity. Instead, it can concentrate computational effort where it is most likely to matter. That is why heuristics are central to efficient search. This slide asks us to evaluate common search algorithms used in artificial intelligence problem solving, and that requires more than simply naming algorithms. Evaluation means looking at what a search strategy is designed to do, what kind of problem it supports, and where its strengths and limitations become important. Search algorithms can be used for pathfinding, optimization, and decision making, but those purposes are not identical. A method that works well for finding a route through a structured space may not be the best method for tuning a system or choosing among competing actions. When we evaluate search algorithms, we are examining the fit between the problem and the strategy used to solve it. This slide highlights pathfinding as one major area where search algorithms are used. In pathfinding, the AI system must move from a starting point toward a goal by considering possible routes through a space. That space might be physical, logical, or abstract, but the underlying structure is still made of states and transitions. The search algorithm determines how the system explores those routes and how it decides which route should be considered next. If the problem requires a reliable path through a clearly defined structure, then the search method must examine alternatives without becoming overwhelmed. Optimization is another important use of search algorithms. In an optimization problem, the system is not only trying to find a valid answer, it is trying to find a better answer according to some criterion. That criterion might involve cost, time, accuracy, distance, efficiency, or another measure defined by the problem. This is where evaluating search strategies becomes especially important because some methods may reach a solution quickly but not necessarily the strongest solution, while others may examine more possibilities. The appropriate approach depends on whether the situation demands the best possible outcome, a near optimal outcome, or a practical solution within limited resources. The slide also connects search algorithms to decision making. Decision making problems require the system to compare possible actions and determine which one best advances the goal. This is closely related to search because every action can move the system into a new state, and each new state may open or close future possibilities. A search algorithm helps the system reason through those consequences. It gives the decision process structure, so the system is not merely reacting to the current condition, but considering how choices connect across a sequence of possible outcomes. When we evaluate common search algorithms, we also need to consider their strengths and limitations. A strength might be completeness, meaning the method can find a solution if one exists under the conditions of the problem. Another strength might be efficiency, meaning the method can reach a useful outcome without excessive computation. A limitation might appear when the search space grows too large, when the algorithm lacks guidance, or when the problem requires more flexibility than the strategy provides. These strengths and limitations determine whether a search method is realistic for a real AI problem. This is why the slide emphasizes that evaluating search algorithms helps determine appropriate approaches. There is no single search strategy that is automatically best for every situation. The right choice depends on the structure and demands of the problem. If the problem space is small, a simpler strategy may be enough. If the space is large, complex, or costly to explore, then a more guided approach may be necessary. If the goal involves optimization rather than simply reaching any valid solution, the search method must be judged by how well it balances quality and computational effort. Search algorithms are important for solving complex AI problems because they provide a way to manage uncertainty and possibility. Many AI tasks involve situations where the solution cannot be directly observed or immediately calculated. The system must explore, compare, and select among alternatives. Without a search strategy, that process can become disorganized or computationally unrealistic. With an appropriate search algorithm, the system can move through the problem space in a disciplined way and make progress toward a goal. The final point on this slide is that selecting the right strategy depends on the structure and demands of the problem. That means we should not evaluate algorithms in isolation. We should ask what the problem looks like, how large the search space is, whether the goal is pathfinding, optimization, or decision making, and what constraints affect the search process. A graduate level understanding of search requires this kind of judgment. We need to understand when algorithms are useful, why they differ, and how their strengths and limitations shape intelligent problem solving in artificial intelligence. This slide focuses on the role of a pattern search in optimization and decision making, and it brings the module into a more advanced view of search. Up to this point, we have treated search as a method for moving through states and transition in a structured problem space. Pattern search extends that idea by applying search to optimization problems, where the system may not have a simple path, a clear formula, or an explicit model that tells it what the best solution should be. Instead, the system explores possible adjustments and looks for patterns in how those adjustments improve or weaken the result. That makes pattern search important when AI systems must work through spaces where the best answer has to be discovered through evaluation. The slide states that pattern search extends traditional search methods, and that extension matters because not every AI problem can be represented as a neat set of discrete steps. Traditional search often works well when states and transitions can be defined clearly. Pattern search is useful when the problem space is more continuous or complex, meaning the solution may involve adjusting values, tuning parameters, or exploring combinations that do not fit neatly into a simple sequence of moves. The system still searches, but the search is directed toward improving a solution rather than merely reaching a final destination. This is why the slide emphasizes continuous and complex problem spacing. In a continuous space, there may be many possible values between two options, not just a limited set of choices. That creates a different challenge because the system cannot simply list every possible state and inspect them one by one. A complex problem space may also involve interactions among many variables, where changing one part of the solution affects the usefulness of another part. Pattern search helps manage this complexity by exploring change in a structured way and observing whether those changes move the system toward a better outcome. The slide notes that pattern search is useful when optimal solutions must be identified without explicit models. This is a powerful idea in AI because many real problems do not come with a perfect mathematical description. We may be able to test whether one solution performs better than another, but we may not have a direct equation that tells us exactly where the optimum is. Pattern search can operate in that setting because it does not depend on having a complete explicit model in advance. Instead, it can evaluate candidate solutions, compare performance, and adjust the search based on what those evaluations reveal. Parameter tuning is one practical area where this role becomes clear. In many AI systems, performance depends on selecting appropriate settings or values. These settings can influence how a model behaves, how an optimization process proceeds, or how a system balances competing demands. Pattern search can help explore those settings by testing different configurations and looking for improvements. The goal is not to choose values at random, but to search in a way that uses observed performance to guide further exploration. The slide also identifies system optimization as an important application. System optimization involves improving how a system performs according to some objective, such as reducing cost, increasing efficiency, improving accuracy, or balancing several goals at once. Pattern search supports this process by helping the system move toward better configurations, even when the best configuration is not obvious. In complex systems, the relationship between decisions and outcomes may be difficult to predict fully. Pattern search gives the system a method for probing that relationship and using the results to make better choices. The final idea on the slide is that pattern search contributes to adaptive decision making in AI systems. Adaptive decision making requires a system to respond to changing information, changing conditions, or changing performance needs. Pattern search supports adaptation because it allows the system to continue evaluating alternatives rather than relying on a single fixed answer. When conditions shift, the system may need to adjust parameters, reconsider trade-offs, or search for a new configuration that performs better under the current circumstances. In that sense, pattern search helps AI systems remain flexible in environments where the best decision may depend on ongoing evaluation. When we bring these points together, pattern search shows how search and optimization are closely connected. Search is not only about finding a path from a start state to a goal state. It can also be about improving a solution, tuning a system, and supporting decisions when the problem space is too complex for direct calculation. Pattern search extends traditional search by giving AI a way to operate in continuous and complex spaces, especially when explicit models are unavailable.